The work presented below is about the identification, tuning, and analysis of the Chimarrão's water temperature control using the feedback control strategy. It was done by academics Adilson Borges Gutierrez and Marília Sartori, participants in the Group L, as a partial grade requirement for the discipline Instrumentation and Chemical Process Control from Chemical Engineering course of the Universidade Federal do Rio Grande. Before we start, what is a chimarrão? It's a typical hot beverage consumed in certain regions of Brazil, very similar to a tea, although drunk with specific utensils that we call bomba and cuia. The bomba is used to suck the water, while the cuia or gourd is used to storage the beverage and the water. The herb used is erva mate, produced mostly in south region of Brazil. It's important to maintain the water always hot but not too hot to burn. That's why we choose a temperature of 75 Celsius degrees. The objective was to identify the control parameters in open and closed loop and tuning using feedback control of a system in strategies P, PY, and PYD for water temperature control intended to Chimarrão by using Arduino, aiming to establish system at temperature of 75 Celsius degrees. We used a relay, a digital temperature sensor DSL 18B20, one boiler of 220 volts, jumpers, an analog temperature sensor PT100, one nano Arduino board with USB cable, a pitcher for water storage, and a protoboard. PT100 calibration and analysis of boiler's potency. Firstly, we calibrated the PT100 sensor as opposed to DSL 18B20 sensor to obtain the reading value given in Celsius degrees. We performed then a curve, obtaining the calibration equation which was used in the program. We analyzed the potency of the boiler with the goal to determine the effective potency, being 662.14 watts. Methods of identification in open and closed loop. The controlled variable in the system is the water temperature, and the manipulated variable is the boiler's potency. So, to make the identification in open loop system, water was heated with a share of 7% of the effective boiler potency until it reached a steady state. This temperature was approximately 59 Celsius degrees. When reached this stage, we provided a step in the variable, understood by a variation in action to check how the system's response would behave, expecting the same to reach a new steady state. This second action was 20% of effective potency, and the temperature reached was approximately 87 Celsius degrees. The time between one chart and another was 10.012 seconds, whereas the time waited to the performance of this step was 1 hour. The experiment was performed in triplicate and obtained the following charts. With these data, we did an average of the values, calculating the proportional gain of the process Kp, corresponding to the temperature variation per variation of the potency, the time constant tau, corresponding to 63% of the final temperature variation, and delay time Td. Using the co-income table, we calculated controller gain parameter, Kc, full time constant, tau I, and derivative time constant, tau D, for open loop, obtaining the results shown. To calculate the closed loop parameters by Ziegler-Nichols table, we needed to find the last gain, Ku, and the last period, Pu, corresponding to the last possible values before the system becomes unstable. To find these parameters, we carried out the identification in closed loop in Scilab software using the XCOS tools, varying the gain of the process until the system presented constant oscillation result. The last gain in this situation was 20.67 watts per Celsius degrees, and the last period corresponding to the distance between a crystal and another was 3,190 milliseconds. With Ku and Pu values, we find the values of the controller gain, Kc, full time constant tau I, and derivative time constant tau d for the closed loop. Tuning with feedback control. To accomplish tuning of the system strategy in the proportional P, proportional integral Py, and proportional integral derivative Pyd, we use the Arduino platform while maintaining a set point at 75 Celsius degrees. For proportional control, we use the parameter Kc obtained from the identification in open loop and from the identification in closed loop, presenting the following curves. Curve P open loop. When approaching the curve, we analyze that the system has not reached set point, maintaining an offset of 1.14 Celsius degrees approximately with open loop parameters. Curve P closed loop. When approaching the curve, we analyze that the system has not reached the set point, maintaining an offset of 7.56 Celsius degrees with the closed loop parameters. Then, we perform the Py and Pyd control in both strategies again, but now we use the speed equation form, viewing eliminates the window problem. We obtain the following graphs and their respective approaches using Kc, tau I, and tau d parameters. Curve Py open loop. Analyzing the graph's approaches, we can see that the temperature varies around the set point. Curve Pyd open loop. Analyzing the graph's approaches, we can see that the temperature varies around the set point. Curve Py closed loop. Analyzing the graph's approaches, we can see that the temperature varies around the set point. Curve Pyd closed loop. Analyzing the graph's approaches, we can see that the temperature varies around the set point. Comparison of results in open and closed loop. In order to compare the experiments presented, we calculated the performance parameters of each process, always based on the same reference, namely YAE, YSE, YTAE, and YTSE. The objective would be to find the control that had the lowest values of the parameters. Between the open loop controllers, the one who showed the best turn was Pyd, while between the closed loop controllers, the one who showed the best turn was also Pyd control. Results and discussion. With all the experiments, it was possible to identify which control performed better from the previously mentioned criteria. Viewing the table, we find that the best turn was with Pyd control strategy using the parameters obtained in open loop, followed by Pyd control strategy using the parameters defined in closed loop. Analyzing the criteria parameters, namely overshoot, setting time, rising time, decay ratio, and offset, the best turn was also Pyd in open loop control, followed by Pyd in the closed loop control. Prediction of temperature data using the mathematical model. A prediction of the temperature values was performed using the proportional control strategy parameters identified in open loop from the use of a mathematical model of the process, so we observed from the charts the model validation. Here we have the link to observe the video in real-time operation of the process with proportional feedback control. these are the bibliography used. Thanks.